Hello everyone, my name is Weitao. Today, Brandon Liu and I are going to present the paper, Jump-Oriented Programming, a new class of code reuse attack. Since there are numbers of defenses have been proposed to either detect or prevent return-oriented programming-based attack, such as dynamic integrity measurements and attestation, detecting return-oriented program malicious code, and the returnless approach. All those defenses are based on the fact is that attackers always use return instruction to achieve attack. To get around above defenses, this paper presents an alternative attack paradigm called jump-oriented programming, which use similar idea of ROP, but use indirect jump instruction to do gadget discovery and chaining instead of return instruction. We will talk about GOP in more detail later. Let's start from some backgrounds. In most modern computer systems, the memory organized as a stack. When a function calls, the operating system will first push caller's address into the stack, then allocate some memory for list local variables. As shown in this diagram, we can see that the local buffer is on the top of the memory, and the caller's return address is below it. Thus, when attacker overflows the buffer with certain value, then attacker can modify the return address to let the control flow go to attacker's shell code. In this example, by using the strcpy function, the attacker can easily modify the return address. However, this attack approach can be easily prohibited by write XOR execute guarantee. Write XOR execute guarantee means every page in process or kernel's address space may be either writable or executable, but not both. Thus, if we want to write shellcode in buffer, then we are not able to execute it. If we want to execute it, then we are not able to write shellcode into buffer. But this defense method also can be circumvented. Instead of let program return to shellcode in data segments, attacker can let program return to some existing codes from libraries. This method called return-oriented programming. The idea is using some small instruction sequence ending with a return instruction called gadgets to do the programming. There are intended gadgets and unintended gadgets. Intended gadgets are instruction sequence that the developer means for it, such like a return statement in the end of a function. Unintended gadgets means some sequence that are not intended to be there by developer. Unintended gadgets exist due to the variable length of instructions. We can interpret same machine code into different meaning by different offset. Based on these facts, we can find a lot of useful gadgets which can do loading from memory, loading into memory, arithmetic operations, and system call. That means return-oriented programming can perform truly complete behavior. In an attack, attacker needs to find those gadgets and push this gadget's address into memory stack. And since return instruction actually is pop address to EIP register, so the stack pointer takes the character of programming counter. Thus, each return instruction will read a new gadget's address and run the corresponding gadgets, then go to another gadget by return instruction and keep going. But since return-oriented programming always use return instruction to do the instruction jump, and all gadgets address stored in a consecutive memory space, thus there are many defenses based on those characteristics, such like detecting the consecutive execution of small instruction sequence, each ending with a return, detecting a ROP execution by observing continuously popping return address that always point to the same specific memory space, and eliminating all return instruction in a program. To circumvent those defenses, this paper used a jump-oriented programming, and Brandon will explain jump-oriented programming in more detail.
So now I'll give a brief overview of jump-oriented programming, or JOP. In JOP, we have two types of gadgets, a single dispatcher gadget and multiple functional gadgets. We first jump to the dispatcher gadget by exploiting the same vulnerabilities as in ROP. The dispatcher gadget maintains a variable that points to an address of another gadget in the dispatch table. This dispatch table can be put into memory using a buffer overflow or some other technique. Each of these addresses in the dispatch table points to a functional gadget. The functional gadgets do some computation and must jump back to the dispatcher gadget, and then the cycle continues. The dispatcher gadget is any code that advances a virtual program counter in a predictable way and then jumps to the dereferenced address stored in the program counter. So let's take a look at this concrete example. In this example, the virtual program counter is a register EDX. And every time the dispatcher gadget is invoked, EDX is incremented by 4. EDX points to an entry in our dispatch table. When we dereference EDX, we get the address of a functional gadget. And one interesting thing to note is that based on the way we change EDX in the dispatcher gadget, the dispatch table actually doesn't have to be contiguous. Functional gadgets in JOP are very similar to ROP gadgets. Usually they do a few instructions such as loads, stores, adds and subtracts, and even system calls. But what's different from ROP gadgets is that functional gadgets in JOP must end with a jump instruction back to the dispatcher gadget. This means that the register used for the jump instruction must contain the dispatcher gadget address, or it must be able to be dereferenced to get the dispatcher address. In our example, ESI must contain the address of the dispatcher gadget. And if you dereference EDI, that value must also be the address of the dispatcher gadget. And interestingly, you can also use the call instruction instead of jump. Even though call pushes a return address onto the stack, it's irrelevant because JOP doesn't use return addresses anyways. Now that we know about dispatcher gadgets and functional gadgets, how do we find them? First, we can search through for potential gadgets by performing a linear scan through the executable region of a binary. And since x86 uses variable length instructions, there may be unintended instructions that can be used as gadgets. These are sequences of bytes that by using a different offset than the intended offset, they look like instructions and can be interpreted as instructions. In a library such as libc, there are thousands of potential gadgets, so we want to filter them by the most useful ones. We use heuristics to find the most useful gadgets. So some heuristics may be that gadgets cannot destroy their own jump target, gadgets cannot disturb the jump targets of subsequent gadgets, and that the dispatcher gadget should use the least use register as its virtual program counter. And this is because functional gadgets cannot use whatever register the dispatcher gadget uses as to not corrupt the virtual program counter. So the authors implemented JOP using Debian Linux and libc. They found around 31,000 potential gadgets. And after using heuristics, they narrowed this down to 150 load gadgets, 33 write gadgets, and so on. And this is enough gadgets to be Turing complete. So the attack can be any arbitrary program. And the simplest way to launch a shell is to call a library function, but that would actually create an artificial stack frame, and it runs into the risk of being detected by anti-ROP defenses. Instead, on x86 Linux machines, to perform a system call, you can set EAX to the system call number, and then set EBX, ECX, and EDX to the call parameters, and then execute the sysenter instruction. And using this, the attacker can perform a system call to invoke a shell. Now, lastly, I'll discuss a bit on JOP and talk about future work. So it's much more difficult to craft a JOP attack than a ROP attack. And this is because JOP relies on certain registers to serve as some state, such as the virtual program counter and the register to jump back to the dispatcher gadget. And this adds restrictions to the sequence of gadgets that can be assembled. And to help make JOP attacks easier, people have created tools such as JOP Rocket that aid in the finding of JOP gadgets. Now, second, because we use x86, we found many gadgets due to unintended instructions. However, in RISC-V or MIPS that use fixed length instructions, there may actually not be enough gadgets for the attack to be Turing complete. So future work must be done to determine if JOP is expressive enough in these architectures. And third, if we look at both ROP and JOP, the underlying issue is allowing entry to any address in an executable program or library. So to defend against them, we need to enforce control flow integrity, or CFI. Now, however, CFI requires complex code analysis, which is difficult for large code bases such as libc. And CFI has not seen widespread deployment because of performance issues in real-time enforcement. So thus, further work must be done to provide more efficient defenses to ROP and JOP. Thank you for listening. This concludes our presentation, and we'll be happy to answer any questions.